Hi, this is lecture 15 of M223. So, as I have said in the last session, in this lecture 15 we will see some examples, we will see some computations related to sequences, that is all. So, first kind of sequence that we have seen is the notion of bounded sequences. So, what is a bounded sequence? A sequence A from N to R is said to be bounded if I can find a positive real number m such that mod a n is less than or equal to m for every n belongs to n. If this is the case, then we say that this sequence A, we usually write it as a n, this is a bounded sequence and this is one bound for this sequence. One can also say that this image, if it is a bounded subset of R, I mean these two are actually same thing. Image being a bounded subset of R is same thing as saying that there is an element m such that this is model a n is less than or equal to m for every n belongs to n. So, this is the definition of bounded sequence. Let us do some example. So, let us take a sequence n square. So, now we will see whether this is a bounded sequence or not. What does it mean to say that this sequence is bounded? There is an element m positive such that mod n square is less than or equal to m for every n belongs to n. See, this n square is already positive, so we can actually remove this mod. So, we are looking for an element m positive such that n square is less than m for every n belongs to n. Now, this n and m both are positive. So, I have said this sometime before also, if I have two real numbers a and b such both are positive such that a square is less than or equal to b square, this implies a is less than or equal to b. So, here n square is less than or equal to m, this implies what? N is less than or equal to root m for every n belongs to n. What does this say? For every n belongs to n, I have this inequality. This means the set of natural numbers is bounded, but we have already seen before that this set n is unbounded. So, one cannot find an element m positive such that n is less than or equal to m for every n belongs to n. So, this says this sequence is an unbounded sequence. So, this is very simple. We have used the property of n being a unbounded subset of R to conclude that this sequence is an unbounded sequence. Let us do one more example. So, consider the sequence 2 power n belongs to n. So, now we are checking whether this is a bounded sequence or not. Again the same thing, suppose this is a bounded sequence, then we need to get an element m positive such that 2 power n is less than or equal to m for every n belongs to n. Now, see, observe, I cannot apply the same idea as this, because I know that this taking square root is easy, but here I have to take if I have to remove this n here, I have to take nth root. Again to the right hand side of this inequality there will be some n part which I do not want. See, if you are taking square root here, here there is no n part, but here if I take nth root, I will get this n will go anyways, but here I get nth root of m, which is good for nothing. So, what do is we make use of the notion of what is called the logarithm. I said I will discuss this function in detail when we do integration, but for now we use the idea of logarithm. I am assuming you know some properties of logarithm. If you do not know, go back and check Wikipedia what are the properties of logarithm function. and we apply that here. So, first of all, this is an increasing function. So, if I have two elements with a less than or equal to b, log of this should be less than log of this. So, because logarithm is an increasing function, we have this property. See, we are trying to find an element m such that it has this property. Suppose this is true, then we have this. Why? Because log is an increasing function. If a less than b, log a will be less than log b. Now, I am assuming you know some property of logarithm. Logarithm of a times b is logarithm of a plus logarithm of b. So, log of 2 power n with the same idea, this is same thing as log 2 plus log 2 n times, that is n times log 2 less than or equal to log m. See, these two are same. I am just writing down what does this mean. This means log 2 power n is equal to n log 2, that is all it means. Now, one can remove this log part from here and write that n is less than or equal to log m by log 2. Now, here there is no n part, and on the right side we have just n. This is true for all n belongs to n. So, what does this say? This says again the set n is bounded above by log m by log 2. By log m by log 2. So, this is a contradiction we have already seen before just now that this n is an unbounded subset of R. So, this cannot be the case. There is no element m positive such that n is less than or equal to log m by log 2. See, observe the difference. In the first example, it was almost straightforward. There is just a power 2. So, we have taken square root on the both sides, and this implies n is less than or equal to m for every n belongs to n. This says that the set n is a bounded subset of R. We have seen before that this n is unbounded. So, this is a contradiction. There can be no m positive with this property. So, this is a unbounded sequence. Similarly, here suppose we try to do take nth root here. See, we know nth root exists, that we have seen when we deal with when we have discussed the notion of completeness of the order. We have proved that root 2 is an element of R, and then we said using the same idea one can also talk about nth root of 2 for every n belongs to n, and then we said nth root of any positive number exists for any n belongs to n. So, one can of course take nth root on both sides, then we can get rid of this n, but on the right side we will still have the n part, that is not good for us. So, we have to take help of this log function, and because log is increasing function, this implies log 2 power n less than log m. This is just the property of logarithm function. Log a b is equal to log a plus log b. So, here I am multiplying 2 n times. So, the multiplication on the here turns into addition when we take the image. So, log 2 power n is equal to log 2 plus log 2 plus log 2 n times, that is n times log 2. And here I am not changing anything, this is still log m only, and log 2 comes here. So, n is less than or equal to log m by log 2 for every n belongs to n. This says the set n is bounded above by this quantity, but we already know that n is a unbounded subset of R. So, there can be no m positive with this property. So, this is a unbounded sequence of R. Let us do one more example. So, let us consider the sequence. Again n belongs to n. So, now we are trying to see whether this sequence is a bounded sequence or not. In the previous two example we tried to see that it is we try to assume it is a bounded sequence and we got contradiction. So, maybe this is also an unbounded sequence, because I am writing just next to those two sequences, but let us see if this is a bounded sequence or an unbounded sequence. So let us at least write down some first few elements of this. For n is equal to 1, what is this? 2 times 1 plus 1, that is I think it is 3 by 1 square is 1 as far as I know. 1 minus 3 is minus 2, so minus 3 by 2, nice. For n is equal to 2, 2 times 2 is 4, 4 plus 1 is 5, 5 by 2 square is 4, 4 minus 3 is 1, so this is 5. What about 3, 2 times 3 is 6, 6 plus 1 is 7, then I forgot what is this. So we got at least 2 elements. So first element is it is negative. Look at the other elements. Suppose n is greater than or equal to 2. This says this element is already positive. N is greater than or equal to 2 implies n square is greater than or equal to 4. N square minus 3 is greater than or equal to 4 minus 3, that is equal to 1. So this denominator is already positive. It is greater than 1 and this is already positive. So once I cross 2, every element in this sequence is positive. So suppose we are looking for boundedness of this. So this is already bounded below by this element at least. Every element is positive. This is just the only negative element. So this is bounded below by this element. Now see, that's why I didn't write down what is the third element. Once I cross 2, I already know this is everything is positive, so I didn't write down this. Now bounded below is clear. Is it bounded above? How do we know? So now we are looking for an element m positive such that is less than or equal to m for every n belongs to n, but we can ignore the first element, because if m is positive, this is already less than m, right? Maybe for n greater than or equal to 2 we can take, right? This element for n is equal to 1 is already negative, so this will be anyways less than m for any positive m. So I am just taking for from n greater than or equal to 2. Now let us write down what does this mean. So this is same thing as saying 2n plus 1 less than or equal to m times n square minus 3m. See, we do not know how to proceed, so we are just trying to write down this in a neat way. So what do we have? The 1 plus 3m is less than or equal to m times n square minus 2n. I do not know what to do from here. So this says something like this has to be true. Okay, if there is m positive such that this is true, then we should have this condition, right? I am just writing down what does this mean and what does this mean. Now there are many real numbers. How many m's should I check for this? It is not clear. So this again, I want this to be true for all n belongs to n. Let us see if this is true for m is equal to 1. Maybe. See, it may be true, may not be true, but we will get some idea. We have to apply. See, we want this to be true for every n belongs to n. We are looking for some element m such that this inequality is true for every n belongs to n. So we have to start at some place, right? We are starting at the 1. So we will try to substitute m is equal to 1 here and then see if it is true or not. If it is not true, we might get some idea of how do I change this m so that this is true. We will get some information. So we will try to substitute m is equal to 1 here and see what happens. For m is equal to 1, what do we have? We have here this is 4, 1 plus 3 is 4, less than or equal to n square minus 2n. So this is something as saying n times n minus 2 is greater than or equal to 4. So now we are seeing if n times n minus 2 is greater than 4 for every n greater than 2. So is it true? How do we know that? Suppose n is equal to 2, then we have 2 times 2 minus 2, this is 0, so 0 is greater than or equal to 4, this is wrong. but suppose we realize the condition that n is equal to 2, then what happens? Then we have to take n is equal to 3. Do we have that? Do we have that possibility here? 3 times 3 minus 2, that is 3 times 1 greater than or equal to 4. No, this is also wrong. So for n is equal to 2 it is wrong, for n is equal to 3 it is wrong. What about 4? Let us try for 4. Is it true for n is equal to 4? 4 times 4 minus 2 is equal to 4 times 2 is greater than or equal to 4. This is 8. Oh, this is true. Okay, nice. So what about n is equal to 5? So should I go on doing this forever? N is equal to 4, 5, 6 and so on. That is one good idea, but then this full session will be allotted to writing down substituting n is equal to 4, 5, 6 and so on. So let us not do that. Let us see if n greater than or equal to n greater than 4, do we have this inequality? N greater than 4, does it imply n times n minus 2 is greater than 4? Right, this is what we want, or equal to 4. See, if n is greater than 4, n minus 2 is greater than 2, right? I am just applying minus 2 on both sides, I am adding, so the inequality does not change. So n minus 2 is greater than 2. So all I am doing is, so we are just multiplying these two inequalities. So this gives n times n minus 2 is greater than or equal to 4 times 2. This is 8. Unfortunately, this is it may be the case that, see, if this is true, then this is always true. But all we can conclude from here is this is greater than or equal to 8. So we have n times n minus 2 is greater than 8. So 8 is already greater than or equal to 4. So we have this inequality. So whenever n is greater than 4, we have this inequality. So we were expecting that this is true for every n greater than or equal to 2, but we have only realized that for 2, 3, n is equal to 2, n is equal to 3, this is not going to be not going to hold. So 2n plus 1 by n square minus 3 is less than or equal to 1 for n greater than or equal to 5, right? For 4 also we have seen that we can ignore that 4 thing. Okay, so what do we have? This is true for every n greater than or equal to 5. So this says the set A5, A6, A7, this so on, this is bounded, right? That bounded by 1, that is what it means. Now, but we do not know anything about the set A1, A2, A3, A4. This we do not know anything about. That these elements may not be bounded by 1, that is the problem. But any finite set is bounded. So finite set union, this set should be bounded. So this is bounded subset because it is a finite set. This is bounded because of this condition. So union of these two sets is the bounded subset, and what is the union of these two? Simply A of n. So this concludes that this sequence, whatever I have mentioned here, this is a bounded sequence, not by 1, because it is true only from 5, 6, 7 or maybe from 4 also, but that is okay. Except the finite set, the image is bounded by 1. So this finite set is bounded, and this union, this is a bounded subset of R. So this sequence 2n plus 1 by n square minus 3 is a bounded sequence of R. Nice. So now we have seen 2 examples of unbounded sequences, 1 example of bounded sequences. Maybe that should be sufficient to discuss about bounded sequences. Let us try to see for convergence sequences. So what is a convergence sequence? A sequence an is said to be convergence sequence if there exists a L belongs to R with certain conditions. What is it? Given epsilon positive, there is n belongs to n such that an minus L is less than epsilon for every n greater than or equal to n. So this is the definition of the sequence an converging to this element L belongs to R. We have seen some property of convergent sequences. What is it? Any convergent sequence should be a bounded sequence. So we have seen 3 sequences before. One can check for the convergence of those 3 sequences, but 2 of them are already unbounded, so there is no point of looking for the convergence of those 2 sequences. What are those? 2 power n, it is unbounded, so there is no way that this is going to converge, and n square is unbounded, so this is also not going to converge. This sequence is bounded by 1 except the first 3-4 elements. So there is some slight chance that this is a convergent sequence. I mean, it is not necessary that every bounded sequence is a convergent sequence, that we have already mentioned before, but because this is bounded, there is a slight chance and we do not want to lose a chance. So we will check whether this is a convergent sequence or not. So now we are checking for convergence of the sequence 2n plus 1 by n square minus 3. So now the first question is, this sequence, suppose it is convergent, to what element does it converge? That is the main problem. So now we first have to guess the element to which this sequence converge. What we have is we have one information. What is it? Except the first 3-4 elements, all these elements are in between 0 and 1. Right, that is what you have seen here. Maybe this 4 also can come here, but anyways, except the first few elements, everything is less than 1. A5, A6, A7, everything is somewhere here, not necessarily in the way that I have written, but all elements are here. I have given some exercise that says, if I have a sequence that is bounded between 2 elements, and if it converges, it should converge to some element in this domain, right. Let me write down the statement. Suppose an is bounded by say a and b, and if converge, an converges to L, then this implies L belongs to closed AB. This should be true for every n belongs to n. So here we are ignoring the first 4 elements, we are considering the new sequence. Further this is true, or maybe the assumption that we are making here we can change slightly. Suppose a less than or equal to n less than or equal to b for every n greater than or equal to k for some fixed k, then if it is convergent, that element L should be in between a and b. This is also the same statement. So here what we have is, every element of this except the first 4 elements are in between 0 and 1. So if it is convergent, then it should be somewhere here, it should the convergence should be somewhere here. Now there are so many elements from between 0 and 1, so what element should I choose to look for convergence? That is not clear. So let us try to see if we can reduce the bound by slightly by some portion, so that maybe the search area for convergence may be reduced to some extent, right. Looking for the element to which this sequence converges between 0 and 1 may be slightly difficult than looking for convergence between 0 and say half, right. The area is reduced to half, so maybe it is easier to check for some element here to which this sequence converges. So let us try to see if 1 is really the maximum bound that we can write down for this sequence. Let us see. So we are looking for some element m belongs to 0, 1 such that 2n plus 1 by n square minus 3 is less than or equal to m. See, m is equal to 1 option is already, we have already seen that this is true. So let us try if we can do something about m is equal to half. This may not be true, but we can just try, I mean we do not lose anything. So we are looking to see whether this is true for all n belongs to n or except the first few elements, as in the case of m is equal to 1. So this is same thing as saying that 4n plus 2 less than or equal to n square minus 3, and this is same thing as saying 5 n square minus 4n, that is equal to n times n minus 4. So we are looking for we are trying to see whether n times n minus 4 is greater than 5 for every n equal to 4 maybe, right? Till 4 it's always it's anyways 1 is not the bound, so 1 by 2 will also be not a bound. So maybe for 4 let us see 4 times 4 minus 4, this is 0, so for 4 it is not true, n is equal to 4 it is not true. What about n is equal to 5? For n is equal to 5, 5 times 5 minus 4, this is already 1, so 5 is less than or equal to 5, so this is true. Even if I take n greater than or equal to 5, we will still have, we replace this element by we can just put n in place of that, n minus 4 is already positive, so n times n minus 4 is always greater than 5. So 1 by 2 is a bound for the sequence that starts at 5. So whatever I have mentioned here, this from 5, one can actually put A4 here, this is true for A4 also, but from A5 I know for sure that it is less than or equal to 1 by 2. So what do you conclude from here? Suppose the sequence an converge, this is 0 and 1 and this is half. After A5 every element is of the sequence is between in this interval. So if it is convergent, it should converge to some element between 0 and half. So now we have to look for some element in this interval to which that sequence converge. Now again let us not settle for just this reduction in the bound. We were looking for from 0 to 1, then just in one step we have reduced the bound by half, right? We have reduced the search area by half. Let us see if we can still reduce the search area. What about 1 by 3? Do we have this n square minus 3 less than or equal to 1 by 3? Do we have this inequality? So what does this say? This says 6n plus 3 less than or equal to n square minus 3. Again the same thing as saying 6 less than or equal to n square minus, so 6 is less than or equal to n times n minus 6. Now we are looking, can I find an element k such that after n is greater than k we have this inequality. So for 5 this is true, so let us check for 5. So if n is equal to 5, 5 minus 6 is minus 1, so this is minus 5, is this inequality is not true, so n is equal to 5 it is false. What about 6? For n is equal to 6, 6 times 6 minus 6 is 0, so this is greater than 6, it is false. What about n is equal to 7? 7 minus 6, 7 minus 6 is 1, 7 times 1 is 7, this is true. So it says that this is actually true for n greater than or equal to 7, right? That is what you have seen here. So if we have stopped at the bound 1 and we have to look for the convergence, we have to look in the interval 0 to 1. Now if it is convergent, it should converge to some element between 0 and 1 by 3 only. The bound is reduced by so much, it was 1 previously, we made it to half, then we made it to 1 by 3. So but still let us not settle down at this, let us try more whether we can reduce the bound by some amount more less than this. One can do, one can keep on going for 1 by 4, 1 by 5, 1 by 6 and all, that may be a bad idea. So let us just ask, fix some k belongs to n and let us see whether this is true, n square minus 3 1 by k. Is this true? So what do we have? 2nk plus k less than or equal to n square minus 3. This is same thing as saying 3 plus k less than or equal to n square minus 2nk. So 3 plus k less than or equal to n times n minus 2k. Okay, so now the question is, can I find an element L belongs to n such that for every n greater than or equal to L that this is true. See, one obvious thing to take care of is that this has to be positive element. So n should always be greater than 2k, otherwise this is negative, but this is positive, so this is anyways not going to work. So let us take the next element after 2k. What comes after 2k? 2k plus 1. So what about n is equal to 2k plus 1? Do we have this inequality? Here I am writing the same thing, 3 plus k less than or equal to n is 2k plus 1, so I am writing that here 2k plus 1 times n minus 2k is just 1, so I am just not writing that. So now the question is, do we have this inequality for every k? Is it true? So this is something as saying 3 minus 1 less than or equal to 2k minus k, this is 2 less than or equal to k. So whenever k is greater than or equal to 2, then this is always true. Then this is true, there is an element L belongs to n such that whenever n is greater than or equal to 4, we have this inequality. So we have 2n plus 1 by n square minus 3 less than or equal to 1 by k for all k belongs to n. See, this needs some explanation. This is not true for all n. Whenever I fix k, I can find some element n belongs to n, or maybe some L belongs to n, such that whenever n is greater than or equal to L, this element is less than 1 by k. This is what we have seen, right? Whenever you fix some k, I can find some element L such that for every n greater than or equal to L, this is the case. We actually have some L here. L is equal to just 2k plus 1. That's what you have seen here, right? But that's not relevant. We need some L such that whenever n is greater than or equal to L, we need this inequality. So now the bound, whatever the bound we have started with 0, 1, it will keep on reducing to 1 by 2, 1 by 3, 1 by 4, so on. So now we don't know what to do. If it is convergent, it is not going to be in 1 by 2 because the bound is reduced, so it will be in maybe 1 by 3 also. There also it may not be the case because it may be in 1 by 4, it may be in 1 by 5. Observe, in all these intervals one element is common, that is for sure, 0 is a common element. So maybe if this is convergent, maybe this should converge to 0, it may be true, you do not know. So do we have that situation 2n plus 1 by n square minus 3, does it converge to 0? See, this is how I want you to think about guessing some element, because see, one can always make a wild guess, but that may not work always. This idea of trying to see, whenever you talk about convergence of a sequence, we should know a priori that it is a bounded sequence. It will be helpful if I know that it is a bounded sequence. Then the limit that I am checking for will be in that bound only. That in this case, except the first few elements, every element is bounded by 0 and 1. So I know if it is convergent, it should be converging to some element here. So then I will just pick some element and then see if it is working or not. So knowing the bound of a sequence is always helpful if you are looking for the convergence. Now because looking for the bound 1 was easy, except the first 4 elements, everything was in between these. We were just trying to see whether we can reduce the bound by some amount, and this was also easy, except the first 7 elements, everything is bounded between 0 and half. That's for 1 by 3, whatever. So we have seen that for every k belongs to n, I can always find some L such that after L this is the bound. So 1 by k is bound for a very large portion of the sequence, and that says if it is convergent it should converge to the only possible element is 0. See, it may not converge, that is a different thing, but if it is convergent it should converge to 0. I mean, this is not a proof, but this is giving me some idea of what element should I choose. So I am choosing 0 because 0 is the only element that belongs to all intervals. That if I take say 1 by 19, 1 by 19 is not an element of say 0 comma 1 by 20, right. Whatever I have said here, this sequence will be less than 1 by 20 after certain stage. So in that case, if it is convergent, it can converge to 1 by 19, right, because 1 by 19 is not in this interval. Every element is in this interval, but 1 by 19 is not even in this interval also. Yeah. So the only possibility if it is convergent is to 0. So let us just check that. So to check the convergence, what we need to do is the following: given epsilon positive, there is a n belongs to n, such that whenever n is equal to n, 2n plus 1 by n square minus 3 is less than epsilon. Now one good thing that we have done before is we have tried to see the bound, this bound. One can use this bound in this situation. How? We know before by Archimedes property that given epsilon positive, there is a element k belongs to n such that 1 by k less than epsilon. So see, we have know that given epsilon positive, one can find a k belongs to n such that 1 by k is less than epsilon. This is the Archimedes property. So one can use this k, given epsilon positive, one can use this k, and for this k we already know that this is true, right. 2n plus 1 by n square minus 3 is less than 1 by k for every n greater than or equal to 2k plus 1. So given epsilon positive, we have n is equal to 2k plus 1 such that for every n greater than n, we have 2n plus 1 by n square minus 3 less than 1 by k, which is less than epsilon. So this says this sequence converges to 0. So you should observe that I did not make a guess, random guess related to the regarding the sequence. We have made use of the result that says if I have a sequence that is that lies in some interval, at least except the first few elements, then if it converges, it should converge to some element in the same bound. Suppose I have two elements, say m comma m, such that an is in between m and m, at least for after certain k, then if it converges to some element L, that L should be between m and m. This is what we have used. So we have seen that this sequence is bounded by 0 and 1. So if it is convergent, the limit should be between 0 and 1. Then we have seen we can reduce the bound to by half. So if this is convergent, the limit should be between 0 and half. We have reduced the bound again further, and then we have seen the only possible element is 0. See, this calculation of bound was helpful here also, right. We have this took only 2 steps. Given epsilon positive, we already have a k belongs to n such that 1 by k is less than epsilon, but this 1 by k we have seen here. 1 by k is upper bound for this sequence except the first 2 elements, and so we have this situation. So this sequence converges to 0, and that is all. So let us do one more example. possibility of convergence? We do not know. See, even though we know the sequence is bounded, it is not very clear whether it is a convergent sequence or not. It is not true always. So this sequence was bounded, so we were hoping that it converges, and it converges. That is that's fine. So let us take one more sequence that we know it is bounded. So let us take the sequence 1 by 2 power n. First of all, is it a bounded sequence or not? That is a question. So we are looking for some element m belongs to m positive, such that 1 by 2n is less than or equal to m for every n belongs to n. Is there m positive such that 1 by 2 power n is less than m for every n belongs to n. Suppose this is the case. See, we have seen already before that 2 power n is positive always. So this is also positive. So we have this condition. Suppose we prove that for every n belongs to n, this is the case. Then if I know that this sequence converge, it should converge to some element in 0 comma m. So let us first see the bound first. So one obvious choice for m is 1, m is equal to 1. Let us see why this is true. So 2 power n is greater than 1 for every n belongs to n. So 1 by 2 power n is less than 1 for every n belongs to n. So m is equal to 1 is one bound. So if this is convergent, it should converge to some element in 0 and 1. And the same trick, we should look for some element here to which this sequence converge. Whatever I have done in case of in the previous case, let us try to do the same thing here also. Let us see if we can reduce the bound by some amount. Do we have that 1 by 2 power n is less than or equal to 1 by 2 for every n belongs to n? Do we have this case? For this to be true, what we want is 2 less than 2 power n for every n belongs to n. This is always true, right? For n is equal to 1, this is 2. For n is equal to 2, this is 2 square is 4, and by induction one can always prove that this is the case. So nice, happy thing is that this sequence is entirely inside 0 comma half. So if this sequence is convergent, it should converge to some element in this. Let us not settle down here. Let us see. It may be converged to some element, it may be bounded by 1 by 3 also, right? Who knows? So 1 by 2 power n less than 1 by 3 for every n belongs to n. Is it the case? So 3 less than or equal to 2 power n for every n belongs to n. So we are checking whether this is true or not. Let us check for n is equal to 1. For n is equal to 1, this is 2 power 1 is 2. Okay, this is not true for n is equal to 1. What about n is equal to 2? For n is equal to 2, this is 4 is greater than 3. Oh, this is correct. For n is equal to 3, that is 8, it is always true. Then one can look for induction and then see for every n greater than or equal to 2, we have this condition. So except the first element, every element lies in this interval. Nice. So let us see if I can still reduce the bound by some amount. Again, let us see, fixing some element k belongs to n. Let us see if we can find some element L belongs to n such that 1 by 2 power n is less than 1 by k for every n greater than L. This is what we are looking for. As I said, this is all positive, so I am removing this modulus thing. So we are looking for this condition. Fixing some element k, can I find an element L belongs to n such that whenever n is greater than L, this is true. And this is same thing as saying k is less than 2 power n. Again, now we apply the log, we take use of the log function. So log k less than n times log 2. So log k by log 2 less than n. that is what we want, right. Fixing k, we have this element such that whenever n is less than that, we have this inequality. See, here we are using the log is increasing function, that is why we can just go back and forth. So, this says for every k belongs to n, we have this condition. So, for the sequence 1 by 2n, the bound is getting reduced at each step. So, again the same idea as before, it says if at all this sequence is convergent, it should converge to some element, it should converge to the element 0. So, if it is convergent, it should converge to 0 only, because this cannot converge to 1 by 19 for the same reason that I mentioned before, because after a certain stage every element here is less than 1 by 29. So, the sequence cannot converge to 1 by 19, there is a large gap. So, this is one possibility, and how do I know that this is true? Again same trick. Once I get a nice bound in this case, in this way, convergence checking for convergence is actually easy. How do you do that? Given epsilon positive, I already have an element k belongs to n such that 1 by k such that 1 by k is less than epsilon, right. This is Archimedean property. Now, for k for epsilon positive, one can find and for this k, one can find L belongs to n such that whenever n is greater than or equal to L, 1 by 2 power n is less than 1 by k, and because 1 by k is less than epsilon, one can write down this. So, this says given epsilon positive, there is a L belongs to n such that for every n greater than L, 1 by 2 power n is less than epsilon. This says 1 by 2n converges to 0. See, this is how I suggest you to think about convergence of a sequence. Looking for some random elements is not a good idea. Once you know the bound for a sequence, it will be slightly easier. So, that is about convergence sequences, and let us do one Cauchy sequence and then we will stop this session. Some computation of Cauchy sequence. So, now we are checking for a sequence to be Cauchy sequence. Given a sequence, how do I check if it is a Cauchy sequence or not? For that I need to some sequence, and what are the sequence that I am going to write down, it is good if I already know that it is a convergence sequence, because every convergence sequence is Cauchy sequence, that we already know how to do that. So, let us make use of that result and see that some sequence is Cauchy sequence. So, one very basic example of a convergence sequence is 1 by n. 1 by n converges to 0. This we have seen before in detail. So, let us see that. So, that is this is a Cauchy sequence. One can just use that result and code the result and say this is a Cauchy sequence. But let us just rewrite the proof again. How do I prove this is a Cauchy sequence? Given epsilon positive, I need to find an element n belongs to n such that for every m comma n greater than or equal to n, 1 by m minus 1 by n is less than epsilon. Right, this is what I am supposed to produce. This I have to produce this element n belongs to n such that 1 by m minus 1 by n is less than epsilon. Now, see, we already know that this converges to 0. So, given epsilon positive, one can always find some n belongs to n such that 1 by n is less than epsilon for every n greater than or equal to n. So, maybe one can use the same n here. So, that says what? 1 by m minus 1 by n. It is not clear what this says. So, we have to write down this 1 by m minus 1 by n in terms of 1 by n and 1 by m. See, observe that this is less than or equal to 1 by m plus 1 by n, right. These are two positive elements. I am just adding two positive elements is of course greater than the difference. So, 1 by m is less than epsilon, 1 by n is also less than epsilon. So, this is equal to 2 epsilon. So, once I cross this n for every n comma m equal to n, we have this difference is bounded by 2 epsilon, but we want epsilon here, and you know what to do. Given epsilon positive, we got this thing. Suppose we want, so that implies that we get 2 epsilon here. Suppose we want epsilon here, what do we need to do? We need to start here by epsilon by 2. So, here we get epsilon by 2, and we get epsilon here. So, that is a small trick that we have used that before multiple times already. So, that says this sequence 1 by n is a Cauchy sequence, and so that is all for today's session. In the next session, we will see some other examples about continuous functions, uniform continuous functions, and in the notes I will add some more examples of Cauchy sequences and Convergence sequences. We will add some more, but as the course progress, we will this list of examples will keep on increasing. That whenever we get some interesting example, we will just put in the lecture 15 in the lecture notes. Yeah, that is all for today. See you in the next session.